Hello everyone, welcome to lecture 12. In lecture 12, we'll talk about laboratory measurement method, which is in the chapter 9 of our textbook. So in this lecture, we'll cover the section 9.1 to 9.5, except 9.4. So let's talk about the preliminary measurement concept. So in this section, it tells about the principles and the guideline that you have to keep in mind when you design your experiment. So principles of uncertainties. First, the measurement. But the measurement always affects the measurand. So that means that in the process that you want to monitor or to measure, as soon as you're participating in the measurement, so like installing the sensors, your sensors or some excitation that's produced by the sensors will affect the result, the measurement. For example, the system, sometimes also the system of your testing device can affect the property of the measurement, property of the soil. Induction in coils of the resonant column alters the measurement of the intrinsic attenuation. So in the RCTS, they use the coil and magnet driving head. And this coil and magnet has inherent counter EMF effects. So because of this electromagnetic effect, it affects the attenuation measurement. Second, the coupling with the peripheral device. So electronic device has its own frequency response to the measurement. So for example, the oscilloscope that you're using it, also that takes some current, so it's gonna affect your measurement. The voltmeter or current meter, right? The ohm meter that you're measuring the V and the I and the R, the resistance, that also affects your measurement as a circuit, the one component in the circuit. The frequency responses of the peripheral devices must be determined and the corrections made, or responses must cancel in well-designed self-healing measurement. An effective alternative is to minimize the use of the peripheral devices by improving the measurement at the lowest possible level. So we'll talk about this one also later. So it's not good having a lot of electronics in your measurement. So maybe like you can minimize as much as you can. That will help to reduce the noise and the bias in your measurement. So careful design of the cells will help the measurement, and proper selection of the transducers and peripheral electronics, also the electrical impedance matching between them, improve the coupling and mechanical impedance matching of the transducers to the medium, and adequate vibration isolation, removal of the electromagnetic noise, and increasing the excitation level without causing nonlinear effects. So these are all will be helpful for to get the reliable signals. One example is this. So this is the active, very direct noise cancelling by using some very simple concept. First, in the left side, here you have a source. This is the ultrasonic transducer. So it generates the P wave. So then the P wave generates and it bounces back at the material and the water interface, and it goes into the receiver. But at the same time, because it's generating some sound wave, the wave goes directly from the source to the receiver. So in here at time 0, you get the direct signal transmitted from the source. But just putting some shield, maybe you can use the OHP film or some paper or plastic to cover and block the P wave transmitted from the source directly. So the wave goes and you are capturing the wave reflected at the interface more with a higher intensity. So you can see that this directly transmitted wave has reduced by this much. And comparing to the previous one, the reflection from the bottom becomes more evident. So this kind of careful design of the cell, careful design of your experiment can improve your signal quality. And the LTI, the time invariant, and the linearity helps the signal processing. The signal analysis and system characterization in the frequency domain presumes the linear and time invariance of response. This linearity allows for superposition during synthesis operations, and time invariance ensures that the solve response from time shift events remains the same. And background noise, the amplitude for small strain measurements may be so small. Analysis and stacking will be useful to cancel the non-coherent noise and ambient white noise and increase the SNR ratio, the signal to noise ratio it's called. In short, it's referred to as the SNR. When you take the sample and measure it in the lab scale, so you always get the single point, and we assume that this sample, the specimen, represents the soil mass for the entire medium. So we have to make sure that your soil sample can represent or not the entire soil medium, and it's called the RAV, representative volume element. Specimen can only capture internal spatial and temporal scales that are compatible with its size. And fresh specimens do not incorporate the effects of diagenetic processes. Even clay may lose some of their memory when sampled. So sampling, when you sample it, you have to take into consideration the disturbance that you're generating in the sample. Let's look at the frequency range of our measurement. In low frequency, the seismic, so this is the seismic or the elastic wave propagation. And when the frequency is low, the scored flow and the low frequency dispersion mechanism is prevailing. And when it's high frequency, as you go towards a high frequency, the Biot mechanisms prevails. And also as the frequency increases, because the wavelength lambda goes down, so it will become close to the internal scale, like the particle size, so that the layers or the grain scattering can be quite significant. In the laboratory method, among the laboratory methods, people use the torsional simple shear so that you can apply very low frequency regime, the low frequency excitation, and this is almost like quasi-static. So it's like you have a specimen and then you're applying some torsion back and forth and oscillation of that torsion to look at the quasi-static response. So you're applying some strain and you can measure the force, or you can apply the force and you can measure the displacement of the strain. And resonant column is in the frequency range of 10 to several hundred hertz, and band element ranges from the 1 kilohertz to 10 kilohertz. And geophysics, the geophysical survey method in field, in general, that's about like 10 to 100 hertz, and earthquake is less than like 20 hertz in general. The main energy is in this kind of a frequency range. So the frequency range of the laboratory measurement may be different than those that affect the propagation in the field or generated in the geophysical study. So the proper data interpretation is required to consider the frequency effect. And small strain behavior of particulate material is governed by the environmental parameters such as the stress state and the degree of saturation, and pore fluid chemistry, and initial fabric, and diagenetic alteration. So then when we do the laboratory testing, what kind of cells are we using widely? First is the true triaxial. So here we can control the vertical stress and one horizontal stress and the other horizontal stress. So sigma 1, sigma 2, and sigma 3. Right? So independently we can control the stress. That's why we call it a true triaxial test. And ideal to study the separate contribution of different stresses and complex stress histories, but inadequate for the attenuation measurement because it's a cubical size. An asymmetric or cylindrical specimen surrounded by a thin latex membrane and confined in a pressure vessel is also widely used, right? This is most widely used. And when we apply the axial, the longitudinal loading, or torsional loading like this, there's no geometric spreading. And torsional, flexural, and longitudinal mode. Flexural mode is like when you have a specimen, you're applying the force like this, so it becomes like this. So it oscillates like this when you're, and this is called a flexural mode. You can measure the resonance and free vibration decay and pulse going back and forth reflections. May allow for deviatory loading. So you can have the deviatory loading different from the radial or the radial stress. And you can use the coherent magnet system for the excitation and the band element or the mechanical impact. And oidometric cells has a rigid wall. So it's like you can have like a metallic the wall that's containing the soil, like a cup, or it can be a plastic. But the oidometric cells typically refers to the cell that doesn't allow the horizontal stress. So it's in the K0 state of stress. Inadequate for the attenuation measurement because you get the geometric spreading and also the reflections all around the cell. But it's ideal to control the environmental variables such as temperature or the stress. Typically, we instrument the piezo crystals, like the band element or the piezo disc at the top and bottom to capture the wave propagation. As I said, the cylindrical specimen is the simple and the versatile specimen shape because it allows the control of the state of stress and minimal boundary effects and the lack of the geometric spreading. So it allows the material damping evaluation. And also you can apply different modes of the oscillation, the vibration, like torsional vibration and longitudinal vibration and flexural vibration. But the drawbacks are there are some stress gradients in torsion and the flexural excitation. That means that because the bottom is fixed here, this is the fix. And when you apply the torsion, so at the bottom the torsional strain is 0, but at the top the torsional strain will be the maximum. So you have a strain gradient that's biggest at the top and the smallest at the bottom. The velocity dispersion in longitudinal and the flexural excitations. And flexural, the strain gradient is also produced like this because here at the bottom is the strain is 0, but at the top you get the maximum shear strain. So this table shows the typically used transducers and the peripheral electronics, like signal for the source, piezo crystals, electromagnetic drive, the mechanical impact, sparkle laser, the receiver is proximeters. It measures the displacement. And laser also can measure the displacement or velocity. U prime is the velocity and U is displacement. And piezo crystals, piezo film, and geophones measure the velocity. And the hydrophone measures the pressure, so it's like a force or the stress. And the accelerometer measures the acceleration. And for the electronics, signal generator, power amplifier, preamplifier, filter, oscilloscope, or the AD board are used, right? And there are some cables. So then, what are the main difference or the transfer function or the frequency response of the displacement and velocity transducers? Like this. So when you measure the velocity using geophone or proximeters or displacement with the proximeters, so x prime is the velocity and this is the displacement, their response is like this. So as long as the Euro frequency is bigger than maybe like 10 times bigger than the resonant frequency or the characteristic frequency, your response is quite flat. So you don't have to worry about the like sensor specific response, the effect of your sensor. But if you go below than that, you may have to worry about your response can be biased by this your transducer's response. For the accelerometer, this is the accelerometer, typical accelerometer response, and you can see that the frequency range, the range of the frequency for the measurement should be less than 10th of the resonant frequency. So as you go near to the resonant frequency, your response will be amplified because of the amplification in the resonance of your acceleration. So these two are all different response. So when the accelerometer says the resonant frequency is like 10 kilohertz, then if your measurement is less than 1 kilohertz, this is safe. Huh? Okay, now we're gonna talk about and see how the ultrasonic transducer works. Ultrasonic transducers generally have this kind of a schematics. Firstly, you have a piezo material, piezoelectric material, and there's some matching layer to generate the wave with some directivity and without losing some energy. And there's a backing block. Also, the material of the backing block is very important so that you don't get any reflection from the back. And these are the casings. And there's some electric cables that's to excite this piezo material. If the damping layer is high, then your excitation or the generated P wave or the ultrasonic wave will shape like this. And if this matching layer has low damping, then the generated wave will be like this. This kind of ultrasonic transducer or the piezoelectric material shows this kind of the behavior or the characteristic. So when you apply the force, it generates the electricity. It's called the piezoelectricity, and this is discovered by the Pierre Curie, so Madame Curie's husband. And when you apply the current or voltage, also it deforms. So we are using this kind of mechanism to generate the P or ultrasonic wave using this kind of transducers. So ultrasonic transducer or the piezoelectric transducers transform the mechanical energy to the electrical energy or electrical energy to the mechanical energy. So then, let's see the one example of the ultrasonic transducer use of the ultrasonic transducers. This is the source and receiver, and it generates the P wave. And when there's some interface with the impedance mismatch, so here the impedance is much lower than the material, then it will be reflected and captured by the receiver. So you can see that this is just a noise, and you get the high reflection from the bottom here. Okay. And so then we can do some simple exercise. So if you have source and the receiver, so this is the source and receiver transducer, and from here we want to know the depth of the water. So this is the water, and this is the steel plate or the very high impedance material. And here source to bottom, from source bottom to receiver, so from P wave to travel by back and forth by 2z. Okay. Took about 92 microsecond, and we know the velocity is 1500 meter per second, and this is 2z over delta t, so the z will be over 2. So then how much do you get? So it's gonna be 46, and 46 times 100, 1500 times 10 to the 6 will be around, if I get, so it will be around like 69 millimeters. So the depth from the tip of the sensor to the bottom will be around like 70 millimeter. And if there's some object, here, and we don't know the thickness of it, maybe like, let's say that x, and the distance is unknown, but the delta t has reduced by 72 micrometer. So then now this is the z prime, so that z prime will be 1500 times 72 minus 10 to the negative 6 over 2. And this will give you some number, and x will be z minus z prime. So then this is about like 15 millimeter, 1.5 centimeter. So reflection method is based on this kind of just fundamental mechanisms. So you have to pick up the variable time here. So how long it has taken from the zero, the excitation of the P wave. Okay, this is the shows the two-dimensional scanning section of the reflection method. So from the reflection method. So for example, if the transducer is here, the wave will be like, because it will bounce back at the water and sand interface, and then the transmitted wave will go to the bottom, and then it will bounce back, so that you will have one reflection and then another reflection. So this reflection is from what? Water and soil interface, and this reflection is from soil and like bottom interface at here, right? So as you can see, and you can get this kind of a signal as you move horizontally, maybe by like 1 millimeter by 1 millimeter, as shown in here. Maybe it's like 2 millimeter every 2 millimeter. Then you get this signal, and you get another signal, and you get this signal, and you get another signal. You get this reflection and another reflection. And then if you flip this kind of whole cascade of your signal by 90 degree, then you get this. So one signal, you can see that there's some reflection, right? That's from this water and soil interface. And then there are another reflection shown here is from the bottom. Right? And as you move along the x-axis or the horizontally, let's say that you inserted some anomaly, then this P wave, there will be another reflection at the top of the anomaly, okay? The interface between the sand and anomaly. So using this kind of a reflection method, you can detect the location of the anomaly. Okay, let's look at more closely the mechanism and the characteristic of the ultrasonic transducers. Transducers are not point size, so I think I've shown you here. So this whole piezo material deforms like this when you apply the voltage to this material, right? Due to the piezoelectricity. So then whole cross section or the area, the surface of the material will generate the impact to this matching layer. So every point on the face of this piezo material will generate some force to the matching layer, and that will generate the wave and transmit the wave. So here, if this is the piezo and this is the backing material, every point will create this spherical, like half spherical wavefront, right? And here also, and here also. And then what will happen? The wavelet generated at every point at the transducer and medium interface, this wavelet travels, and there will be some interference between this wavefront. So some will be cancelled out and some will be superposed, and then it gets amplified, so that the unique pattern of the amplitude fluctuation occurs in the near field of the transducer. So then what happens is that for a certain amount of distance, the amplitude of the energy is not going away. It's not decreasing fast. But if it's point source, we know that the wavefront will be like spherical, so that as you go further away from the source, the amplitude should decrease by like r square, 1 over r square or something like that, right? But because of the source has some area like this, and this generates wave, this generates wave, and they are all tangled and convoluted together, so that amplitude doesn't decrease for a certain amount of distance. And then it starts to decrease like this. So up to this point, it's called the near field. And after this field, it's called a far field, this point. So the near field can be, so how long will be that near field? That can be calculated using this equation, r squared over lambda, and here the r is the radius here of your transducer. And And in solid, in the near field, strong coupling between the P and S wave. So in the near field, you cannot differentiate the P wave and the S wave because they are all like body wave coupled. But as you further away, then the P wave goes faster and there's S wave following it. So that the P and the S wave are separating, start to separate from the far field. Okay, so another just schematic showing the near field effect. And in near field, you don't, the ultrasonic transducer have a very good directivity, like this. And then in the far field, it's like a spherical wave propagation, so that it kind of propagates with some angle. And when we look at the intensity, or this is the pressure, or you can say that it's the amplitude, the near field for a pair of the identical transducers is studied by aligning the submerged source and receiver transducer and gradually changing the distance between them. So you're fixing this source, and this is the receiver, and you're moving this receiver away from the source. So at 1 millimeter, amplitude was here. At 10 millimeter away, still it's here. At 100 millimeter away, now it's going down like exponentially. So the slopes are very different. So it's kind of a bilinear curve. And at point here is the threshold differentiating the near field zone and the far field zone. So in this experiment, like at around like 70 millimeter, here is the distance between like geometric decay amplitude versus actual distance become apparent when the distance between the transducer exceeds 70 millimeters. So that's kind of within the 70 millimeter, it can be called as a near field. Huh? And directivity is like when you have a piezoelectric material, then how much directivity is made or produced, or it has, shows the directivity. So for example, if it's just a simple like source or point source, it doesn't have the directivity. So the wave will go propagate to the every direction. Right, 160 and a sphere, like a spherical wavefront. But when you have this kind of piezo material with the disc type, then you have some directivity like this. So the amplitude in this zone is much bigger than here. So amplitude will be like this. So a transducer focuses in a certain direction, define the directivity lobes. The conical bounds of the main lobe where radiated energy vanishes defines the divergence angle. So we can also check the directivity of your sample. I'll show you the result soon. The divergence angle should be small to increase the lateral resolution. While a focused and low divergence transducer is preferred in medical ultrasound, like when you do the your exam, the medical exam, they use the ultrasonic sound sensors, and that has a very high directivity. But wide beam may be preferred to detect the off-center reflection with a fixed position transducer. So it's like when you have a sensors that's collecting all the ultrasonic wave reflected all around it, then it's better to have low directivity. So one example is like ultrasonic transducer or ultrasonic sensors at parking lot. So that the one with the light, the green and the red. So when your car is parked, and then it becomes the red, because that captures the reflected wave faster than before when the car is absent. So it becomes green when the reflective wave arrives later, slow, because of the distance is now it's longer. In that case, you don't know where the reflection will be bounced off, so that off-center reflection or the wide beam or low directivity will be preferred. So this is the test result showing the directivity of the typical ultrasonic transducers. You have a source and you're moving the receiver from horizontally from the center of the source. So you can see the amplitude goes down as you go further away horizontally. And here also you can circle around the source of the receiver. And amplitude was the biggest when you're facing parallelly right each other, but as you go off from the center to center line, then the amplitude decreases dramatically. So next topic and the last topic of this lecture is the band element. And I guess that you've heard about the band element a lot. Bender, I recommend you to read some the papers about the band element. It consists of the two layers of piezo material with the metal seam in between, so that you apply, and this piezo material is when you apply the voltage, then the length of this piezoelectrical disc changes, so it can be elongated. And here too, so either you can use the both sides of the piezoelectric material, or you can just use the one side. So just because the one side is elongated, and let's assume that the other one is just keeping the constant length, then because of they are attached together to match the compatibility, it becomes, it will be the other way. Yeah. It will deform this direction. So this becomes the longer, and while this is just the same. And when you apply, if you apply like the negative voltage like this, then this will be shortened, so that it will deform like if I can exaggerate, it will be like this. So it can be bended if you install it as a cantilever beam. So you're fixing the one end of the bend element by embedding it in the material. Then it will deform like this, so that you can generate the S wave to this direction. But as you can see, it also generates the P wave because you are pushing it to this direction or this direction. And generally, you coat the band element with some polyurethane or some plastic material, and embedded in some like driver or some plastic screw, and mounted on your cell. So let's look at the band element types and how they are aligned. So in parallel type, I think you have to look at the website, the piezo.com. and it shows the it will have the better and the more detailed explanation. And there's an expo bender and YPO bender, and I think one of them is the parallel type and the other one will be the series type. So what they and it's about how they are aligned. Let me try to explain it. The parallel type is like it's pulled in this direction and also pulled in, could be maybe this direction. So the piezoelectric material has a polarity. And then if you have voltage applied here, it should be the parallel, so it should be the same direction. Then when you apply the voltage inside this metal shim, then when you look at this material, it's pulled in this direction. At the bottom is the plus, and the minus or the 0 is at the top. So then it could be elongated. So it's gonna be elongated like this. Elongation. And what about the bottom one? Now, when you have a polarity like this, and at the top surface, the voltage, positive voltage is applied, but at the bottom face, there's no voltage. So it's now the polarity of the applied voltage is opposite. So it's gonna be shortened. Right? So then what will happen? This will elongate, but this will be shortened, so that it's gonna deform like this. So that's how you operate the parallel type. So you apply the voltage at the middle metal shim, the positive voltage, or it could be negative voltage, either way. In series type, you're using only the this material, and this will be in this direction. Okay. And now it can be, and the other is you don't apply any voltage. So here the voltage is applied here, so we can apply the positive voltage in this direction. So then in this phase, then it will be what? Shortened, right? According to that, to be consistent with this parallel model, it will be shortened. But this will be to stay the same, because here is the 0 and also here is the 0. Okay. So then it will be reflected like this. But the difference is that they are here with the same, like for example, this is the same 10 volt and it's the same 10 volt. It's the same 10 volt. One material is elongated and the other material is shortened, so that your deflection is much bigger than here, right? So the deflection delta parallel is bigger than the series. So many people, in literature, people suggest to use the parallel type as a source and the series type as a receiver. But anyhow, you can use the parallel type, the both for the source and receiver, and the series type for the source and receiver. From my experience, it doesn't affect the result that much. So then how do we install? We have a band element at the top and bottom, and here in this diagram, they use the top band element as a source and the bottom band element as a receiver. So signal generator applies some maybe like sine signal or like square wave, and this will excite, right? And the S wave will propagate, and receiver will capture it, and also this will be acquired in the oscilloscope. And there are some P wave generated to this direction. So this P wave can bounce back and can reflect. The reflected P wave can be captured in the receiver band element. Or if the vibration is too much, then the wave can go through the cap and the wall and the other bottom cap, and it can be captured in the receiver too. So there could be some other noises because of that kind of a reflective wave. So the typical setup here is that you have a signal generator, and this applies this is the source band element, and receiver band element acquires the S wave, and that acquired signal is amplified in the filter and also captured in the oscilloscope. And I think this figure shows that the reflective wave. So you get the reflective wave at here. Band element generates the two P wave side lobes normal to their plane and an S wave frontal lobe. Saturated soil P P over Vs is stress dependent and may exceed 20. For soil subjected to low effective stress, P reflected from the cell may interfere with the S wave arrival. Then what kind of input signal excitation do we use? When we have a bender that's embedded in the cantilever beam, we can apply whatever the source signal, but depending on the mass of the band element and the extrusion length, it will have different resonant frequency, right? So the resonant frequency of the bender will be function of mass and the protrusion length, and also the soil stiffness. So if you apply like sine signal like this or the impulse signal like this, the bender wouldn't move like that. So that the output, here the received signal is very small because the bender didn't move enough to generate the sufficient energy. But as the frequency goes down, you can see the 12 kilohertz, 4 kilohertz, now the signal is more clear. This means that at 4 kilohertz, 4 kilohertz was the biggest, it gives you the biggest amplitude. That means that the soil stiffness may have the resonant frequency of the 4 kilohertz, close to that. And also the band element also have the frequency close to that value. So actually this bender are embedded in the soil. Actually the resonant frequency will be a combination or kind of integrated together by the bender characteristic and the soil characteristic. So initially when people found the band element and suggested methods using the band element, they recommended this kind of a single cycle of the sinusoidal wave for the excitation. But as time goes by, the people found that the resonance of the soil can be too much different depending on the soil, right? You can have the clay soil, which is very soft, and you can have like gravelly soil that has really like high stiffness. So then you cannot define the proper frequency for the sinusoidal wave. So instead of that, just using the step signal that contains the high frequency and the low frequency everything, then it will provide the enough energy for the excitation, and then your output signal will be very clear too. So yep, as you can see also, the signals are very dispersive. Here it's really like sharp, but the received signal is much wider, right? It has a low frequency component. Even though you apply the 4 kHz frequency, the received signal can have like the frequency range less than 4 kHz, right? So the waves are dispersive, wave propagation. So then it's difficult to get the phase velocity. So instead of that, we have to look at the group velocity. So then when we determine the group velocity, it's better and easier to pick up the arrival time when the rising is very steep. Steep rising helps arrival time picking. So, and when you use this kind of a step signal, because it contains the low frequency to high frequency, actually it contains all the frequency components, so that you can generate it can contain some high frequency content in your signal, so it gives you the steep rising in the arrival and acquired transmitted signal. So then, how do we determine the first arrival? This has long been a very difficult question to answer. Recently, when you read the paper by Jong-Sup Lee and Santa Marina, and they kind of concluded that you can pick up this C, the zero after first inflection, as an arrival time, when the H is the tip-to-tip distance. Actually, before, the travel distance was hard to define. Actually, before, when we used the sinusoidal excitation like this, 3/2 length of the tip here, tip is removed. So the distance, the distance travel distance is, if this is the L minus 0 times tip length times 2. But this is the old method. People don't use it anymore. Now that, because that in that time we didn't know where the wave is generated. So that from the cantilever beam theory, when you have this kind of a bender and it's deflecting like this, we are thinking that the S wave is generated at some point here, at 3/2, 2/3, the length of the tip, protrusion length. But now that people are just using the tip-to-tip distance, because it's more simple, and it was also correct. It's proven to be correct to just use the tip-to-tip distance and getting the first the 0 point after the first inflection here. Yep. And please review these papers. And when we have whole electronics, peripheral electronics around the specimen for signal generation and signal acquisition, these peripheral electronics add their response, frequency response to your measurement. So each intermediate component adds a frequency-dependent phase shift and attenuation to the signal, thus the frequency response of all intermediate system is captured in the measurement as well. So when you apply the input signal with some certain voltage and the rising time, your electronics will add its own frequency response, and the band element will have its own frequency response, and soil will have a transfer function in the system, and the output band element and the peripheral electronics, and it's gonna be the resulting signal. So it would be quite complex to consider and remove all this kind of effect. So it's recommended to have the minimal electronics in your measurement system, and then you have to always verify your system whether your system gives you the reliable measurement. Okay, thank you for listening.